Well, welcome to Fitting Models. This lesson can be found in two of our curriculum. You'll find it at the beginning of Algebra 2 because it's foundational to all of the different models that we go through in that curriculum. But you'll also find it near the end of the data science curriculum as an optional lesson that you can go into. After you've taught scatter plots, you might want to jump into this lesson to show students how they can write their own equations and learn how to fit some models, and then maybe head into some nonlinear after that as well. So let's jump in and see what this is about. We start off in this lesson just with some lizards, just small section of our animals data set at the shelter, and look at a scatter plot of those lizards and have the students look and see if they see any pattern with this scatter plot. Depending on how much you have talked about the vocabulary that you've used so far, let them talk about whether they see a negative slope, a negative correlation here, except for that one little lizard over here that was adopted rather quickly, that was small. But the rest of them, there seems to be a pattern that the heavier they get, they got adopted quicker. Um, Now, and then you go on and say, well, if a 2-pound lizard arrived, how long would you predict that it would take for that lizard to be adopted? Talk about what are they doing to come up with that answer. Most would kind of draw this line up here at 2 and say, looks like based on this cloud of points here that I see this pattern going to, that I don't know if I follow this y-axis up, it looks like somewhere around 9, 10, you would get some different numbers there. Talk to them about how did you make your prediction? Did you draw a line through that? And then in the workbook page, we'll have them take a ruler and draw a line through that cloud of points and describe how they came up with that line, what they think that slope is, but a couple points did they pick to go through. You might get a couple of different students doing different things. And here's an example of that. Joe and Cy did that, and they came up with two different models for these lizards. And that's exactly what we're going to get. Any line that goes through this cloud of points is going to be called a model. And we're going to use this model to help us make predictions. That's the whole reason we come up with a model. We want to say, well, if a lizard that's 2 pounds comes in, how long will it be in this shelter before it can get adopted on average? What does it look like? However, as we look at these points, we see they're not all exactly really on this straight line. Any predictor that we get, it's very rare that they're all going to be on whatever model that we can make go through these points. There's going to be some kind of error. And so we have the data and we have our model, but we have some little error that we add to it. But whatever line we can put through that gets closest to these points is going to be our line of best fit. But the whole thing is, well, how do we know that it is the best? How can we come up to what is best? And so as we saw, Joe and Cy had tried their models. They came up with a slope and a y-intercept, and we want to know, well, which of those would be the better model? Well, how do we calculate which is better? How do we calculate which is best? And that's what this lesson takes us to. Just talk with the students first. Of these two models, what would you do to try and decide if Joe's was better than Cy's? How would you measure? What would you measure? And get them to talk. A lot of the students will talk about, well, they might think about how many points are above or below the line. You know, are there the same number of points above or below the line? Does that matter? Do they have to have the same above and below? Maybe you start changing the talk to the distance above and below the lines. Well, what distance? Vertical, horizontal, diagonal? How would we measure that? Well, welcome to Pirates Contract and Function Fit Model. That fit model contract right there does what you see. Here's Joe and Cy's functions that we put in with fit model. Here's the data from the lizards, and it puts that function that they had come up with, their model, straight through that cloud of points. You'll see a line going here showing the the difference between what their model would predict and what actually happened. That's what we see here in the key. These red points are the actual data points, the actual weeks to adopt for those lizards. The line is what's called the residual. The residual is the difference between the actual data and our predicted data from our model. And that's what the blue line represents, is our predicted data. Here's our fit model contract. As you can see, it looks a lot like scatterplot. You have your data set, and then you have the label, and then your X and your Y axis, your explanatory and your response variables. But look, we have a function. Yes, this was Sai's function and Joe's function were entered and defined in the definitions area of Pirate. And we've added them here to put that blue line right through the scatter plot. And so you also see that that scatter plot comes up with something called S and R squared. We're going to focus right now on S, where this is that measure we were looking for. Let's go back here for a second. Our eyes can kind of tell us, ooh, we want to notice with the students, look at this. The y-axis is, the units are by fives here. Here, they're by ones. And so we want to be sure we don't get tricked by that. The distance here is much different than the distance here when it's by ones. We want to be careful as responsible data scientists to catch those kinds of tricky things. But sometimes our eyes can't really tell us which one is better. And so we want to do something as responsible data scientists, get a numerical number that can help us, and that's what S does. We can get a numerical number that can tell us just how good of a fit that model is to those points. S is that standard deviation of those residuals. Remember, residuals is that distance from the model to the point, the actual point, the vertical distance straight down there from, or straight up from the model. And this is the average distance that we are away from the line, if you will. That's what that S gives us. And so if a model goes exactly through every point and there's no residuals whatsoever, you would have a perfect linear line. You would have an S that was 0. The smaller the S is, the better the fit is. The smaller the residuals, the smaller that S is, the better the fit we have. S is expressed always in terms of this Y variable, our response variable. We always put it in units. So, for example, here in the one we've been using, we'd say, for example, if S was 5, then we'd say it's the standard deviation of the residuals is 5 weeks to adoption, always in terms of the Y response variable. Couple of things to remember when you're comparing two models of the same data set, then of course the smaller S would be the better model, and that's how we're going to come back to Joe and Sai, see who had the smaller S, and we can say who was better at predicting and coming up with a better fit for predicting. However, we want to be careful that we are not comparing S models for different data sets. I'll come back here in just a second to the third point, but we have a worksheet that the students do. And here's 1, 2, and 3 from this worksheet. Go through, and they all have an S of 300. That's good, but they're all from 3 different data sets. One has to do with animals at a shelter, another one is Arctic sea ice. And so it doesn't make sense to begin to say, oh, I have an S of 300 here and an S of 300 there. You cannot compare them if they're not from the same data set. Context is extremely important, so be careful with that. And also, another thing to remember is that you have to consider the range. Let's take a look at why. Go back to this one. The animals in the shelter, days to adopt range from 0 to 400. An S of 300 means that I could be off by 300 days. Okay, so I have a prediction of 20 days this animal will be here, but I could be off by 300. You want to bet on that one? Not if it's normally up to 400 days, that they could be there. Oh, dear goodness. That's huge. So the kids here would say, I strongly disagree that this model is a good fit because that range is quite huge. I'm off by 300 days out of 400. That's not very close. However, the next one, if I'm off by 300 square kilometers out of a range that's in the millions, this is almost 4 million to 7.5 million. Now I'm getting pretty darn close. That now is not as far off with that huge range, that large number of square kilometers. So this would be probably strongly agree that that would be a good model. Very different. An SF300 could be strongly agree or strongly disagree. You have to take it into context, what the range is, the context. The third one down there is 2 to 2003. Again, not very good model if you're 300, but better than the first one, but still not great. So let's come back now and look everything we've learned about fit model and what S is, and come back to Cy and Joe. And we give us a closed sentence structure for students to learn how to interpret and how to interpret the error and how to compare. So the error that was for Cy was 5.9 weeks, whereas Joe's error was 1.6 weeks. So with that, we have the comparing models down there at the bottom. You see the structure there. Then Joe's model was better. It had a better S value, so they'll learn to see that. But we also noticed that we talk about that range we were just talking about. The range was 3 to 8 weeks. So 5.9 weeks, that would have been horrible. So you see, we have strongly disagree that that was a good model there. And Joe's model, 1.6 weeks, well, out of 3 to 8, that's still not a great thing. So it maybe not strongly disagree, but that's not a great model. So we kind of came up to the conclusion that neither Cy nor Joe had really drawn the best fit model probably through this cloud of lizard points. Maybe we could do something better, and the students are going to try here in a second. But Joe did better, but by how much better? Do a little lesson in percent change, and so that's what number 2 has the students do on the workbook page. Go back and do a little lesson on or review on percent change if you've had them do that before, and they can find out that they actually can see that Joe's model will have 73% less error than Cy's model. Great math lesson, great review with a lot of algebra lesson review there too coming up. And here's another algebra review. Now we want to fit our own model. Well, let's see. Neither one of those models were great. Let's come up with our own that might be better. And this is great. This was the best part of training with teachers too, is everybody wanted to get the smallest S. There's a lot of competition that goes on here. Let's see who can get the smallest S and get the best fit model that they could find. And so just have them go back to that lizard scatter plot and pick 2 points. It doesn't have to be 2 points that are on the graph here, the data points. It could be any 2 points that they think would make the best line that would go through here, come up with their own y equals mx plus b equation and put it in Pirate. We've got a spot there in the Pirate starter file for lizard. There they would fill that in and run their own fit model and come up with my model here. They've got their own equation, and they'll fill this in and come up with their own S, which was hopefully even better than Joe size. And they have a smaller S value than the other 2. If you are so inclined, then you could continue on here and go in and now address the quadratic, exponential, logarithmic, periodic functions. If you're in Algebra 2, you're going to be doing that. If you're in data science, you can take a look at some additional functions, but have lots of fun fitting functions, fitting your models. It is a lot of fun.